Next up, we have oral presentation 8, Riverside, California, Mission 13 Flight Experiment.
Hi everybody. So I'm very excited to present our experiment to you, the influence of microgravity on the development of Chenopodium quinoa. My name is Audrey Tway, and I will be a senior at John W. North High School next year. And these are two of my co-principal investigators, Alejandro Robles and James Rohde, and they will be attending UC Riverside and UC Berkeley in the fall. Unfortunately, two of our team members could not be here today, Karen Cortina, who will be attending Harvard University, and Hannah Terrell, who will be attending Hamilton University. We are part of Riverside Unified School District in California, and our teacher facilitator was our AP and IB physics teacher, Adam Quall. And throughout this process, we were under the scientific advisement of University of Riverside, California faculty Dr. Qianru Huang and Professor Hailing Zhu. So we are sending quinoa to space, and we're going to send it, or when it comes back down, we will analyze its nutrient content. So first I would like to explain why we decided to choose quinoa as our experiment. Quinoa is what is known as a complete protein, meaning it contains all 9 essential amino acids for human, like a human needs in a day. In addition, it is rich in minerals, vitamins, and fiber. Quinoa is also incredibly versatile, so that makes it easy for astronauts to transport it up to space. It doesn't need light to grow, and it sprouts within 9 days, meaning it can, if it was sent to space in 9 days, astronauts will be able to eat fresh salad because it'll sprout in 9 days. Or it can be eaten in the grain form, so it is also easy to eat that way. So that's why we believe quinoa is the ideal choice for long-term space exploration in terms of food.
So before we got the tube from the SSEP, we had to perform a lot of pilot experiments to ensure that the optimal conditions were reached. We decided that the Type 3 FME mini lab was the best in order to ensure that microgravity was the only factor. We made volume 1 the distilled water, and then volume 2 cotton balls, and then volume 3 is going to be the stopper that makes the growth stop, so that the only factor that is different from the tube here on Earth is microgravity. From here on the picture on the far side of the screen, you can see that when the seeds were not sterilized, there was bacterial growth, so we also had to make sure to find the correct sterilization for the quinoa seeds, as bacterial growth could affect the results of the quinoa sprouts growing. So sterilization was a very important part of the procedure.
So following the experimental procedure, we observed the post-germination stage of quinoa. As you can see in the sprouts in the images, our results yielded healthy growth, with the final image being our post-fixated sprouts. We took results from various intervals throughout our pilot studies. Following 3 days of growth, we were able to determine that our procedure yielded a normal sprout development. As seen in our 25 times and 50 times post-microscopic imaging, there is a normal growth of root hair, which demonstrates healthy plant metabolism.
And then this is what we expect to happen when the quinoa sprouts do come back from space. We're expecting a higher fresh weight content of the quinoa because we looked at prior experiments done in hypergravity, which means more gravity. The plants there was less of them, so we're thinking with less gravity, more plants would grow, as we saw an experiment with more gravity, less plants grew. And then hopefully with quinoa, we can provide nutritional food that can last, because nutrition is such a big issue in space, and finding a food that can provide nutrition over a long time is important, especially for prolonged space missions.
So after our results come back down to space, we will be continuing an analyzation of our quinoa with another UC Riverside professor, Thomas Junkerson, who we recently throughout this process discovered was going to be conducting a similar experiment on the International Space Station, but instead his students are going to be sending tomatoes. So our initial plan was going to send the quinoa to a nutrient analyzing company that would do the nutrient analysis for us, but we discovered that in order to do so, we would need over 100 grams of sample, which we clearly do not in this small tube, and we would also need $2,000, which as a high school, we are unable to fund. So instead, we're going to be looking at the protein content because, like I said earlier, amino acids are a major part of why quinoa is important. So our entire trip here was funded by individuals in our community. So we would like to give a huge thanks to all of those who donated to our trip here halfway across the United States. These are made up of a lot of our high school alumni as well as UC Riverside faculty. Thank you, everybody.
Do we have any questions for this team?
Hi, my name is Erica Ginoario, and I'm from Tampa, Florida. So my question was, how do you guys plan to measure the protein content?
So, very good question. Our plan is to use PCR, or polymerase chain reaction, where we will look at a set of proteins that code for the enzyme, and then we will be able to analyze whether or not there is the equal amount of content in both the ground and the flight experience.
Thank you.
Okay, thank you guys.
Thank you.